Welcome everyone to the May 1, 2020 General Meeting of the Memphis Astronomical Society. Okay, moment of truth. Everybody tell me, how's my audio? We had some issues last week. I'm just going to go ahead and check into the comments section now. So if you would, just before we kick off the presentation for tonight, give me some feedback here. How am I sounding? Am I sounding good? Am I sounding bad? Doing a couple things different this week. I'm not using Firefox like I did last week. I'm actually using Chrome this week. And I did make sure that I plugged my USB microphone in before I started the program. So hopefully my audio is a lot better this week than it was last month when we did this for the first time. And even if it's not, the good news is tonight's talk is recorded. So you're only going to hear me for a little while, and then our presenter we'll chime in, so the audio will be a lot cleaner then. So, but anyway, okay, very good. So how am I sounding? Am I clear? Give me some feedback. Sounds good. Sounds like I'm getting some good feedback here. So awesome, very good. Thanks. Awesome, guys. Appreciate it. Very, very good. All right. Well, welcome once again. And before we get started, I want to take just a second to give a special shout out to John McLaurin and the Seattle Astronomical Society. Some of them I know are joining us tonight, and we just want to extend a warm welcome from Memphis, Tennessee. And we hope you guys are safe, and we hope you guys are making the necessary adjustments during these unprecedented times. Of course, Seattle was one of the cities that was hit really hard early on. The first case, I believe, of coronavirus actually broke out in the city of Seattle. So you guys were really the first ones to have to take the extreme measures to shelter in place, shut down, and then of course the ripple effect just kind of transcended throughout the country. So again, for anybody watching this down the road, we are in the middle of a COVID-19 pandemic, so we are broadcasting live. All of us are been mandated to shelter in place while we ride out this pandemic. I hope everybody is safe. I hope everybody is taking the necessary precautions. The weather's been beautiful here in Memphis the last several days. It was again today. So, hopefully you get some time to get out, get some fresh air, take a walk, enjoy nature a little bit. I was out last night looking at the moon, was out this morning, did a little early morning observing. So, the nice thing about astronomy is hopefully you can get a little astronomy done and still abide by, the CDC's guidelines of sheltering in place and taking the necessary precautions. So anyway, let's go ahead and get started here. I'll load up my presentation. So again, we are the Memphis Astronomical Society, and this is our information. Our website is memphisastro.org, and these are our social media handles. You can find us on Facebook. Our group is at Memphis Astro, and of course we're on YouTube. If you're watching right now, then this is being broadcast live on our YouTube channel, youtube.com, Memphis Astronomical Society. If you haven't already, take a minute to subscribe to our channel. Subscribe to our channel, like this video. Really appreciate you guys taking the time to stop by and participate tonight. And of course, you can find us on Twitter. We try to post updates regularly of any upcoming meetings or observing sessions or anything on Twitter. So it's another way that you can kind of stay in contact with us. And our email is memphisastronomicalsociety@gmail.com. So feel free to shoot us an email if you're interested in becoming a member. If you're a visitor right now and you want to become a regular member, you can email us, or if you just want to drop us a line, we'd love to hear from you. So this is our information. So here's another look at our website, and we've got some great links on our website for those of you who want more information. On the left, you'll see a couple of links on telescopes, anything from aligning a Newtonian to how to buy a telescope. And so we got some great links there on our website. And also on our website in the left is a calendar in the upper left. So, and of course, May, we're still shut down. We're still temporarily shut down and sheltering in place officially as a result of COVID-19. I know this is a tough one because May is a beautiful month, and we've endured some probably less than pleasant weather as well as a long string of canceled observing sessions for the last several months, and now we're starting to get some really nice weather. So our next dark sky observing session was scheduled for May the 16th, and that was actually our Village Creek Star Party, our semi-annual Village Creek Star Party at Village Creek State Park in Wynne, Arkansas. We have canceled that. Actually, we've postponed it until September. So just like Memphis in May, Barbecue Fest has been postponed until the fall. We're postponing our spring events until the fall. So we will have Village Creek possibly in September. We'll get you the date down the road. But as of right now, May 16, we're canceled. May the 23rd was our next dark sky observing session at Burton's. And again, we're canceling that as well. So now, here's the deal, guys. I know things are starting to open up slightly here in Memphis. We're kind of in phase 1 and then eventually phase 2. So officially, we're canceled. We're shut down. We're going to continue to monitor things on a week-by-week basis. We will discuss and reconvene at our next board meeting where we are and kind of make adjustments accordingly. So, but kind of tentatively right now, June the 13th is our next dark sky observing session at Burton's. And we will try to hit that date if we can. You know, we got a lot of time, 6 weeks away. So we'll have another board meeting. We will have obviously another general meeting between now and then. So for now, you're on your own. Feel free to get out, you know, and whenever you can. And tentatively mark your calendars for June the 13th as our next regularly scheduled dark sky observing session at Burton's Sugar Farm. And we will send out announcements as we go. So that's kind of where we are. June 13 and June 20. So we're shut down in May, and we'll see where we are at the end of May as things start to open up and people get back to work. And again, we continue to ride out the COVID-19 pandemic. This whole thing is fluid, so we'll make adjustments as we go. But right now, tentatively, June the 13th and June the 20th. Mark that tentatively as dates that we're targeting for our next dark sky observing sessions. If you want to join the MAS, go to this website, joinmas.com, and just enter your name and your email, and we will add you to our regular weekly email notification list. We try to send something out at least once a week, whether it's an update on our next meeting or observing sessions or videos from past presentations, any value-added information about our organization, about our society. So again, just enter your name and email. We'll add you to our email list, and we'd love to have you. So go to joinmas.com, enter your name and email if you'd like to be added to our email notification list. And if you become a paying member, you get access to our newsletter, which is the Meteorite. And a lot of great information in the Meteorite, such as astrophotography gallery, sky maps. You can see, well, you know, we have each month we have a sky map for constellations and other deep sky objects that are out, as well as articles, and then also the minutes of the MAS Board of Directors meeting. So I'm not going to read them tonight. If you are a paying member, you get access to the Meteorite, and we will have the meeting minutes from our last board meeting in the May edition of the Meteorite. So feel free to read that at your convenience, and it gives you an update kind of our last board meeting and the topics and items that we discussed. So one of the perks of becoming a member. And speaking of members, I want to take a minute to acknowledge a few new members that have been approved recently, going back a couple of months from when we actually shut down. So I'm going to go ahead and just acknowledge Roger, Chuck, and Audrey Evans, who were approved back in March as new members. Congratulations. Welcome to the organization. We are very happy to have you. And then Dennis was approved in April. And interesting story, Dennis actually reached out to us via email. This is after we shut down due to COVID-19. And he was our first member that we actually did electronically. So instead of a handwritten membership application, we actually sent it to him electronically. He filled it out, and then we approved it at the meeting. So Dennis, congratulations. Welcome to our organization. And you have the distinct honor of being the first member who went through the process completely virtually, completely electronically. So yeah, we're making strides here as we shut down for COVID-19. So again, congratulations. Welcome to Roger Chappa, Chuck Evans, Audrey Evans, and Dennis Plafkin. We're very happy to have you a part of our organization. Okay, I'll put links to these two documents at the end of tonight's presentation when I officially post it on our YouTube channel. But if you would like to download a May sky map, we'll have a link to that in the description of this video, as well as a membership application. So if you're interested in becoming a member, just simply click that link, download our membership application, fill it out, and then send it back to us at Memphis Astronomical Society at gmail.com. And again, you can also just email us at memphisastronomicalsociety@gmail.com and say, I want to become a new member. And then we will just email you the membership application. You can fill it out electronically. And then, we'll just do the whole thing virtually, just like we did for Dennis. So anyway, look for a link to these two documents in the description, the May Sky Map and the membership application. We'll have that for you at when we officially post this video at the end of the presentation tonight. So, okay, and that leads us into tonight's topic. And our speaker tonight is Bryan Hill. He is a board member, and he's going to take us on a journey of stars, Stellar Odyssey, so to speak. So we've all heard the children's rhyme, "Twinkle, twinkle, little star, how I wonder what you are." And the truth is, there are quite a few stars in the universe that are very unusual. And I got to tell you, going through this presentation, Bryan's going to cover some classes of stars that I've never heard of before, just very unusual. One of the beauties of astronomy is just some of the strange, bizarre, and wonderful objects that are out there in our galaxy and in our universe. And of course, we're all familiar with the process of stellar evolution that starts from basically a nebular gas cloud until a very dense nugget. So Bryan's going to cover all of that in tonight's presentation. Now, again, since we're doing this virtually, Bryan actually pre-recorded his presentation. I'm going to load it up right now. If you are online, just feel free to add your comments, questions if you have them. I'm just going to be monitoring the comments as we get into tonight's talk and tonight's presentation. So feel free to chime in anytime with any questions, comments, feedback, anything. And we're going to go ahead and kick off the presentation now. And again, guys, thanks for listening. And I'll monitor the comments, and then we'll do a brief Q&A afterwards and attempt to answer any questions or field any comments that you might have. So without further ado, here is Bryan Hill taking us on a stellar odyssey.
Good evening, everybody. I am Bryan, and I'm your presenter for this evening. So I have one question to ask you. What exactly is a star? For astrophysics, the line of "Twinkle, twinkle, little star, how I wonder what you are" has more meaning than expected. Even though this is merely a children's rhyme, it's basically a question that I would think that for everybody, at one point in time, you ask yourself this very question. The Sun, the most well-known star, is merely one in an endless stream of stars. And once observed, the answer to what is a star becomes more complicated than expected. So please join me as we take not only a glimpse at our own star, but also its siblings in the sky. The small or large, the dim and bright, the exotically luring, to the wildly strange, from the far past into the deep future. Let's go ahead and dive into this Stellar Odyssey. 13.8 billion years ago. Of course, this is the image that we've seen countless times. It's of the Big Bang. It's basically an initial singularity theory in which all the mass and space-time of the universe is contained inside of an infinitesimal point. But in actuality, despite what the picture shows, the Big Bang was not an explosion, but an expansion. And with that expansion came the four forces that we all pretty much well know of, well, currently: electromagnetism, the weak and strong force, and also, most importantly, especially for this presentation, gravity. And of course, also those little particles that make up everything, matter. As with most things, there's an evolutionary process with forming a star, as we'll now see. The best example to show this evolutionary process would be using the solar nebula theory, which is basically the theory of how our solar system formed with our sun in the center, the planets orbiting it, and of course all the asteroids and comets. In the early universe, the only matter that would have formed would have been hydrogen and helium. Hydrogen would have made up 75% of the universe, well, the matter in the universe, and helium would have made up 25%. And due to gravity, dust and gas would eventually accumulate into massive clumps, which we call molecular clouds. And here's an example of a molecular cloud over here on the left-hand side. And if you recognize this picture, especially if you're my age, you would know this is called the Pillar of Creation. And this is located in the Eagle Nebula. And I'm pretty sure the first time many of us saw this picture would have been in the 90s in a magazine issue of National Geographic. And these clouds are massive. They are light years in length or diameter, with masses thousands of times greater than that of the Sun. And the gas in the molecular clouds are cold. And in fact, the early universe would have been cold because no stars were in existence yet. Therefore, the clouds would eventually collapse under its own mass into multiple fragments, and which would be stellar nurseries. And these fragments would eventually flatten out into a disk with a bulge in the middle, and at that point, it would be considered a protoplanetary disk. And if you look to the right, here are some examples of this, and these examples are in the Orion Nebula. And in the center of the disk contains most of the mass, and if the gas clumped together accumulates enough mass under pressure, it heats up and eventually becomes a protostar. And in this phase of a star's pre-existence, it lasts between 100,000 to 500,000 years. And you know it's a protostar because it's still obtaining material from the molecular cloud. So this is technically not a star yet. It's basically nothing more than just a hot ball of gas. So basically it's obtaining material and gaining more and more mass, and all the material around it is accreting into what would later become planets, then asteroids and comets. Now, once nuclear fusion commences within its core, then it's technically a star. And once it reaches this point, it's now considered to be in its main sequence. And it will be in main sequence for the majority of its life. Alright, now let's go ahead and get started on the basics of what exactly a star is. What is a star? A star is a massive ball of plasma held together by its own gravity. And plasma is actually nothing more than this heated gas with free moving electrons. So you know how when you look at atoms, you have the proton, the neutron in the center, and then you have the electrons rotating around it? Well, the electrons are actually freely moving. They're no longer connected to the atom itself because of this how hot it is itself. And basically a star has attained enough mass in order to start thermodynamic fusion within its core. And basically, the amount of mass you need to obtain in order to have nuclear fusion is one solar mass. I mean, that's basically how we define it. We just base the parameters based off the mass of our own sun. And basically what happens in fusion is that there's enough heat and enough pressure for two hydrogen atoms to merge and form a helium atom. And as a result of this, you get energy. And this energy is important because this mass of the star is so great that it would just collapse under it. So the energy acts as an equilibrium point. So that way the star just does not collapse, as you can see. So basically, if you look at the star layers, this is a star, you have the corona, then you have the core, and then you have radioactive zone. And basically, in this zone, this is where most of the energy is at. And this is the area that keeps the star from just simply collapsing in on itself. Now that we know what a technical definition of what a star is, let's move on to three categories of stars. The first one would be population 3 stars, and these are known as pure stars. These would have been the first generation of stars which existed about 200 million to 300 million years after the Big Bang. And these stars would have formed from primordial gas, which would have been hydrogen, helium, and trace amounts of lithium and beryllium. And the main reason why these are known as pure stars is because they contain no metals, which makes sense because the first matter that would have been created would have been hydrogen and helium. So these stars have no metals in them whatsoever. And if you want to consider it early universe gigantism, all of these stars would have been high mass stars. So these would have been uber large stars, and they would have been between 60 and 1,000 solar masses. Now, these are still hypothetical, so we have not been able to observe one, and if they did exist, we simply just don't have telescopes powerful enough to see them because they would have been formed in the early, with galaxies still starting out in the early universe. And if you know how space-time works, we can't just simply peer far enough back in time and see an early galaxy with these forming. So these are still hypothetical, but it's logical that these stars would have existed if you follow a pattern which I'm about to show you. Population 2 stars are the oldest known stars. We know that these exist because they are still in existence. And these would have formed from the gases recycled from population 3 stars. And these stars would have been metal poor, meaning that the population 3 stars, when they went supernova, they produced all the first metals in the universe. And the metals would have been primarily lighter metals such as carbon and oxygen. So population 2 stars do have metal in them, and they would mainly be located in the galactic bulge of galaxies. And here's an example of some population 2 stars because this is a globular cluster. So this would mainly be located in the bulge of the galaxy. This finally leads us to population 1 stars, and these are the youngest stars, and they are metal rich, so they have lots of metals in them, and of course they would have formed from the gases left over from population 2 stars. And these are primarily located in the galactic disk. So remember the pattern. Population 3 stars existed maybe around the time galaxies were still forming, maybe, or maybe even just a little bit before. Then you had population 2 stars, and they're in around the galactic bulge of the galaxy. So as the galaxy is still forming, population 3 would have been in the center, population 2 would have been around them, and then you have the population 1 stars, which would have been the disk of the galaxy. So population 3 is in the center, population 2 stars surrounding them, and then the population 1 stars surrounding the population 2 stars. As you can see, stars do come in different colors and sizes. And as said previously, one solar mass equals the mass of our sun, so we just use our sun as a poster boy in order to measure the mass of other stars. And as you can see, they do come in different sizes. We have the red dwarf here, which is only 8% of what the mass of our sun is. And of course, you have red giants, which are 5 times as massive. And then you have blue-white supergiants, which are 150 times as massive. And the star color can also indicate surface temperature. Star classification is basically how stars are classified, and it can be by its size, its luminosity, the surface temperature, and the color of the light it emits. And if you remember how fire works, cooler temperatures the fire will burn in red, while in hotter temperatures the fire will burn in blue. And it works the same way with stars. So the smallest stars, such as an M-class star, which is a red dwarf, which we will talk about, only has a surface temperature of 3200 K, and as a result, it will normally burn in red. Then, of course, you have the sun, which is basically a star basically in the middle range, is a surface temperature of about 5700 K, and it will be yellow. And then, of course, you have the largest supergiants, which is considered an O-class star, and it has a surface temperature of 40,000 K. And color can also indicate age because older stars have a tendency of being red, while younger stars have a tendency of being blue. And also, if you go back to the fact that stars fuse hydrogen into two hydrogen atoms into helium particles, the more massive the star is, the faster they burn up that hydrogen. So actually, the hotter and more massive a star is, the lesser lifespan it has, as you can see here on the chart on the right. So the smallest stars have a low surface temperature and a low luminosity, but they have a longer lifespan. If you look on the right here, you have the red dwarf stars. They live a lot longer than the massive blue supergiants on the right-hand side. Before we move on, I do want to talk about a runner-up in terms of being a star, because unfortunately not all stars are equal. Of course, the runner-up I'm talking about would be brown dwarfs. And these were originally theorized in the 1960s by Shiv S. Kumar, and basically it's an in-between star. Basically the idea is that there has to be something in between a planet and a star, which makes sense because in order to be considered a star, you have to have enough mass in order to start nuclear fusion within its core. But not every massive object is going to be able to do that. So there's going to be objects that are more massive than Jupiter, which is the largest planet in our solar system, yet still smaller than our star, and fusion would not commence. And basically the idea behind it is that these brown dwarfs would be between 10 and 90 times the mass of Jupiter. And a lot of people like to consider Jupiter a failed star, but that would be giving Jupiter too much credit. Because as large as it is, it's nowhere close to having enough mass in order to start fusion within its core. In fact, you would require only 10% of the mass of our sun in order to start nuclear fusion. So if a brown dwarf is between 10 and 90 times the mass of Jupiter, Jupiter does not have a chance of being a star. And we fortunately finally discovered our first one in 1994. And of course, as you can see the image here, this is brown dwarf Gliese 229b, and this was the first one we saw. And the reason why it took us so long is because they are extremely dim. And because of the fact that they do not have nuclear fusion in its core, it does not emit any light in the visible spectrum. All of them are mainly seen in the infrared. And we actually have three classifications of brown dwarfs. First one is L dwarfs, and there's about 1,000 known, and they would have a surface temperature of about 1,500 to 3,000 Kelvin, which is about the same temperature as a pottery oven on its highest setting. Then you go down to T dwarfs. There's about 500 known. They have a surface temperature of about 500 to 1500 Kelvin, which is equivalent to the temperature of a lava flow or even conventional ovens. Then the final one, and which is a Y dwarf, and there's about 17 known. And this is the coldest because it has a surface temperature of about 250 Kelvin to 500 Kelvin, which and that might still sound high, but remember Kelvin is an absolute temperature. So 0 Kelvin is going to be a lot different, and higher is going to be a lot lower than 0 Celsius. So when you get between 250 Kelvin to 500 Kelvin, it'd basically be a warm sunny day to a cold North Pole day. So if it actually had a surface and the radiation and pressure didn't kill you, you could actually walk on this. And what's interesting about brown dwarfs is that this was actually a candidate for what Planet 9 could be. And that's the reason why we have a hard time finding it. Uh, but since it can be seen in the infrared, it's most likely this is not the case. But in the 1980s, a brown dwarf or a red dwarf was considered for a star called Nemesis, which similar to Planet 9, actually explained why we had all these long-range comets coming in and then taking these elliptical 1,000-year orbits, then coming them back around towards our solar system. It was actually a candidate for that. And since then, that's mostly been disproven, but I mean, it is a possibility, so it could either be Planet 9 or Nemesis. But another possibility is that a brown dwarf star could be our closest star, because as everybody knows, the closest known star is Proxima Centauri, which is 4 light years away. But because these brown dwarfs can be so dim, there could be one even closer. So it does not have to be in our solar system. But I mean, if it's like 2.5 light years out, it's going to be hard to see even in infrared. So one of these could actually be a new closest star that's yet to have been discovered. Let's shift gears over to two types of mass stars. Of course, the first one would be the low mass stars. As you can see here with this red or orange dwarf star in a picture, and if you look at the quote, Sloan City wins the race, well, that's very much true for low mass stars, as we will see. Well, let's go back to our poster boy, the Sun, since it's been so good to us, as an example of a low mass star. This star is a G-type star, if you remember going back to star classification, and it's also a population 1 star. So it's a very, even though it formed 4.6 billion years ago, it's still considered to be a young star. And it has 8 known planets, maybe one more to be discovered. And it has one with quote unquote intelligent life, if you want to consider it that, given the fact that its civilization is only about 0.72 on the Cartesian scale, has only stuck on one planet, and with no faster than light travel capability. If you want to consider it intelligent life, okay, we can go ahead and do so. And it will remain in its main sequence, meaning its core is still going through nuclear fusion, uh, fusing hydrogen into helium for about another 4.5 to 5 billion years. But like with all things, the end is nigh. I wonder what planet that is in that picture. Let's shift gears and talk about the Earth, or at least its future slightly. If you look at the picture on the left, the top hand side, you'll see that the Sun as a main sequence star, which it is now, has a diameter of about 0.01 AUs. And AU stands for astronomical units, which is basically a measure of length equivalent to the distance between the Sun and the Earth, which is about 93 million miles. So currently it has a diameter of 1% of that. By the time it becomes a red giant, it'll become 2 AUs in diameter, which is extremely bad, but even before then, things are not looking good. In about 500 to 800 million years, all forms of photosynthesis are no longer possible. So even if plants make it to that point in time, it'll just become so hot and so luminous that it just makes photosynthesis impossible. So eventually all plants will die, and with no plants, no oxygen can be formed, which eventually leads to a chain reaction of having no animals, because animals, if they still breathe oxygen, they'll go extinct. And if they are herbivore with no plants to eat, they'll eventually die out unless they're a carnivore, but once all the herbivores and omnivores die out, there's nothing for the carnivores to eat. Then, of course, in about 1.1 to 1.6 billion years, all the remaining oceans will evaporate, and any remaining single-celled organisms will become extinct. So by this point in time, nothing can live on the Earth. It basically will just go back to being the same way it was when it first formed. There's a giant molten ball of lava and rock. And eventually, Mercury, Venus, and Earth will be engulfed by the swollen sun. So, ashes to ashes, dust to dust. We came from the sun, and we will go back from whence we came. But there's actually a slim chance that the Earth will drift farther away from the sun as it expands. Because when it's orbiting the sun, it's really in a state of equilibrium. Because in the early universe, the Earth was actually farther away from the sun when it first formed than it really was, and it just drifted closer. And then it maintained a stationary orbit. So if the sun were to become bigger, in order to maintain that equilibrium, it might actually start pushing, it might actually start orbiting a little bit further back. The same way how our moon, when it's rotating around the Earth, is slowly rotating away from us. It's a little harder to do that with the sun, but it's not impossible. So there's a slight chance the Earth might actually survive this. Maybe, if we're lucky. Well, what would cause our star to swell up like that? What would cause the sun to go from 0.01 AUs in diameter to 2 AU in diameter? Well, let's speed up the clock a little bit. Let's go forward in time about 4.5 billion years. The sun has been growing slowly, but it hasn't just swollen up to 2 AU yet. Basically, what has happened is that once a star reaches, well, the sun reaches the 9 billion year mark, all the hydrogen in its core it's been using to fuse into helium, it uses it all up. And what ends up happening is that once all the hydrogen in the core is used up, it starts burning the hydrogen in a shell that's surrounding the core. And eventually that just starts heating up the core of the star even more and building up more and more pressure until you eventually reach helium fusion in its core. So basically, it just reaches a, uh ignition point, as you can see on the chart, which says a core helium ignition. So basically, once that starts happening, the hydrogen shell that's around the core starts to expand away from it because now it's being filled up with a new material. And what's happening is that with helium fusion, basically two helium atoms or three are fusing to form carbon. And basically, that goes on for about another 100 million years. And then eventually, all the helium in the core gets used up, and all that's left is carbon. But like with hydrogen, there's a helium shell that forms around the core, and that starts burning until it reaches an ignition point, and then it starts fusing carbon. So basically, or oxygen in its core. So basically, you go from hydrogen to helium to carbon to eventually oxygen. And once the core reaches carbon and oxygen, there's no more fusion. And the reason why this happens is because the star is not massive enough to fuse oxygen into any higher elements. So Once it reaches carbon and oxygen in its core, it's dead. So as stated in the chart, there are actually layers that surround the core itself. So ignore what the chart says because it says carbon oxygen core, but imagine this is a hydrogen core. So basically, once all the hydrogen is uh, is used up, basically there's a hydrogen shell that's surrounding the core, and that starts burning, and that actually heats up the core more and more, and building up enough pressure until the core starts fusing helium into carbon, and then the hydrogen layer gets pushed out, and then the helium layer starts surrounding the core. And then the same thing happens with carbon and or eventually oxygen, and it just keeps building up layers and layers and layers. Then once the carbon and oxygen core, then once it starts fusing oxygen, that's it. Once all the oxygen is used up, that's it. The star is done. And once nuclear fusion stops within the sun's core, then it's no longer producing any energy and it has no counteraction to gravity. So as a result, the star just collapses in on itself, and basically all the outer layers of the star collapse with it and then bounce off the core and just expand into these beautiful planetary nebula. So basically, we're going back from which we came, or at least the star itself will. It started out as a cloud and it goes back into being that. In a lot of ways, it's kind of a form of recycling. And there are estimated to be 20,000 to 50,000 existing in our galaxy currently. And a lot of these are well known, such as the Cat's Eye Nebula and NGC 7662 here. As you can see, all these beautiful clouds, and they are quite beautiful. But the glowing gas eventually fades and disappears within a million years. But if you notice in each picture, there's actually a glowing spot in the center of that. What exactly is that? Well, that white light is a white dwarf star, and that's basically the leftover of of what star that existed there. So basically, that's what our sun will become, a white dwarf star. And basically, what has happened is that the entire mass of the star has now condensed into a ball that's about the size of the Earth. And the reason why it shrank that much is because of the Chandrasekhar limit, which involves electron degeneracy pressure. Basically, what has happened is that because gravity has squashed it down so much that all the electrons that freely move around the atoms, they are just so now compacted that basically they can't move anymore. So that's the reason why it is shrink down so much, because that's how much it need to shrink down in order to stop all electrons from moving in the star. So basically, it's just a giant electron ball now. And it's extremely dense. I mean, it's far denser than the Earth is. And it's still radiating heat because of all that pressure, but that will eventually radiate over trillions of years. But white dwarf stars are merely just remnants of a star. Really, the smallest known stars would be the red dwarf stars, and they only have 10% of the mass of the sun, which is what is required in order for nuclear fusion to happen. And they make up the majority of all discovered stars, which makes sense because all the giants or the high massive stars would have used up most of the gas, and then that would have just had leftover gas. But as long as it had enough mass to reach nuclear fusion, it would become a star. And in fact, Proxima Centauri, which is the closest known star, which is 4 light years away, is a red dwarf star. And these stars can actually live up to be 10 trillion years old. Finally, we're up to the big boys, the high mass stars. And if you look at the quote, the life that burns twice as bright burns half as long, if you've seen Blade Runner, that is very true for high mass stars. And for a candidate, I decided to use a star that has been teasing us recently in the news. I think you know which star I'm very much talking about. I'm wondering if I should just go ahead and say its name 3 times. So let's see Betelgeuse. as it was when it was a main sequence star. Originally, it would have been a B or O type blue star. And this picture here, that's not a Betelgeuse, that's a Rigel, since it's an approximate idea of what it would have originally looked like. It's a population 1 star, so it's a fairly young star, and it's located in the Orion constellation about 642 light years away. It has a diameter of about 1.2 billion kilometers and a mass of about 20 to 30 solar masses, so about 20 to 30 times the mass of our Sun. And it's only about 9 to 10 million years old. And as we've all been hearing recently, it's due to go out. So 9 to 10 million years old versus the 9 billion our Sun is supposed to have. So this star only has about 1% of the lifespan that our Sun has. And it's actually been observed since Ptolemy, which would have been about 200 AD, or possibly even earlier. Which is interesting because if that's the case, because Chinese astronomers actually might have observed this thing 300 years before Ptolemy, and they described it as a yellow star, while Ptolemy saw it as a red star, which if that's the case, we've actually seen this thing go through its phases and actually change color. Betelgeuse is actually a variant of a star. It's called a variable star. And basically, they are stars in which light varies in intensities going through luminosity periods. So it means that it has periods in which it's brighter, and then it dims down, then returns to being bright again. And there's actually multiple types. Pulsating, in which the surface of the star is actually expanding and contracting. Eruptive, in which it suffers a massive flare. Cataclysmic, in which there's this nuclear explosions going on the surface of the star, and then there's eclipsing, in which there's another star that's rotating around the largest star, because most star systems are binary star systems where there are two or maybe even 3 stars. So what could happen is that you have the main large star, and then you have a smaller one, and then as the smaller one rotates in front of it, when we observe it, it seems to be the largest star seems to be losing luminosity because there's an object in front of it. And then there's also rotating because there could be bright spots and dark spots on the star, and that could be causing it to lose luminosity or dim. And Betelgeuse is a pulsating variant. So what is going on? Currently Betelgeuse is an M-class supergiant, and if you remember from the beginning, it started out during its main sequence. It started out as an O-type or B-type blue star, so it shifted. Well, Betelgeuse is known for having a 5.9-year period of dimming, with 425 days of the dimming being in its highest intensity. But since December, it has been in its fatence in 25 years. It's 36% of its normal brightness, which is so great that it's actually noticeable by the naked eye. And if you look at these picture comparisons from January 2019 to December 2019, it's very apparent that it has dimmed down. So, if you say its name 3 times, do you get an explosion? I guess the answer is we'll see. Because since February, its luminosity has begun to steady. And the current explanation for all this fuss about whether or not Betelgeuse is going to explode or not is dust. Because if you go back 2 slides and you saw that picture, well, that artist's conception of Betelgeuse, it's really puffy. And I had stated that it's a pulsating variable star, so its surface is actually expanding and contracting. So as a result of this, it actually sheds material. In fact, it sheds up to 1 Earth mass of material per year. And as a result, it creates dust clouds around the star itself, as you can see in this picture. And as you well know, dust obscures light. So that's basically the current explanation for what's going on. It's just that it is due to the orientation of the star and how we're looking at it. There's just a huge dust cloud that's very thick that's dimming down the luminosity of its light. And eventually, as that dust cloud passes, it would be back up to its normal brightness. So right now, Betelgeuse seems to be fine, and it still has about 100,000 years left. Well, now let's go into its post-main sequence. And for the most part, it's basically the same as low-mass stars, but if you remember, low-mass stars cannot fuse anything in its core once it reaches carbon and oxygen, because it's not massive enough. But high-mass stars, well, at least stars that have over 5 solar masses, can fuse past oxygen. So basically, you go from hydrogen to helium to carbon to oxygen to neon, magnesium, silicon, and then last but not least, iron. And iron is a death sentence because once iron forms in its core, the core becomes inert. And one of the reasons for this is because iron is one of the most stable elements on the periodic table. So it's not really that reactive. So once that happens, the core becomes inert. Then, like with low mass stars, the star doesn't with the core inert, it's not producing any energy anymore, and the star collapses under its own gravity, and we finally have our supernova. The explosion creates a shock wave traveling at about 10,000 kilometers per second. And many of the heavier elements, well, metals such as zinc, silver, tin, gold, mercury, lead, and uranium are actually produced from this. And many of the leftover gases may form into new stars. So, for example, all it would have taken for a solar system to form would have been to be in a molecular cloud. Then maybe there was an older star, probably population 2 star, which was a high mass star, and then that supernovaed, and then all those heavier elements eventually became part of our cloud. And then when our star formed and our planet formed, that's where all these metals came from. They came from the leftover gas from these supernovas. And supernovas have been recorded on Earth since 185 CE or AD. And here's some of the more famous ones would be the 1054 supernova, which was seen by Chinese astronomers, and it was so bright that you could actually see it during the daytime. And since then, once we started observing stars more in the 1960s, we actually pointed a telescope at that same area because we found those old original Chinese records. We actually pointed at the same area of the sky where we saw the supernova from, and we end up seeing the Crab Nebula. Then, of course, there's SN 1987A, which is a supernova in the Large Magellanic Cloud, which is 168 light years from Earth. So basically, we can see supernovas from other galaxies. That's how bright they are. But not everything is good about them, as we will now see. And like always, with the good, you have to take the bad. And the bad would be, well, outside of the explosion, if you're too close, would be a gamma ray burst. And basically what happens is that when the core collapses in a high mass star, a beam burst or jet of gamma rays shoots out from the poles of the star. And it's basically like a jet if you look at the picture on the right hand side. It's basically a jet of gamma rays and basically has radiation throughout the entire spectrum. So it has gamma rays, X-rays, visible light, radio, but most importantly it has gamma rays because these are very, very harmful towards living things. And let me give you an example of a star that we are concerned about. This is WR104, and it's about 7,500 light years away. And this is actually another variant of a star. It's called a Wolf-Rayet star. So basically what has happened is that it's a high mass star in which it has shed its hydrogen outer layers and its helium core is exposed. So if you look at the star on the right, all this gas cloud around it, this is all the hydrogen it had, and this bright spot in the middle, that's actually the core itself. So the star has not gone supernova yet, but but it's on its way out, and it's already shedding its outer layers here. So all this right here in the center, that's a helium core. But if you look at the picture of WR104 on the left, do you notice something strange about it? Maybe the orientation in which the gas is rotating around the star itself? It's pointed directly at us. So there's actually a slim percentage of a chance that when the star novas, it could produce a gamma ray burst. And if it's pointed right at us, we might be hit by it. Now, as I said, there's a small chance that can happen because space is big, and it would take a lucky shot in order to hit us, but there's actually evidence that leads to the fact that we may have already been hit by one. A gamma ray burst may be a possible reason for the Ordovician extinction 440 million years ago, killing 2/3 of all species on the planet. And the reason why this happens is because a direct hit by gamma ray burst can deplete up to 40% of the ozone layer, allowing harmful amounts of ultraviolet radiation to reach the surface. So basically, they think this is one possible explanation, because they've been looking for other ones like a meteorite impact similar to one that killed the dinosaurs, or volcanic activity, and there seems to be no real traces of that. I mean, and those factors could be contributing factors, but a gamma ray burst would not have helped. So that's how dangerous this thing is. This thing, just by being hit by it by a couple seconds, can cause an extinction level event. So we as a species could get our act together, move on to more energy efficient resources, stop polluting the planet, our ozone layer returns to being 100%, and everything's all hunky dory, and then we get hit. And all that hard work just went up in smoke. Sleep well. And like with low mass stars, high mass stars also leave a remnant, or at least currently two types of remnants. Let's start off with the first one, neutron stars. And basically, this thing is even more dense than a white dwarf star. And usually they have a mass between about 1.4 and 3 solar masses. And yet they have shrunk down to a size that's even smaller than the Earth. It only has a radius of about 10 kilometers. So a neutron star goes from being this massive billion-kilometer wide, 20 solar mass, 5 to 10 solar mass star to something that's about the size of a city. And like with white dwarf stars, you have neutron degeneracy pressure. Because with white dwarfs, you have electron degeneracy pressure, in which once all the electrons stop moving, it won't shrink down any further. But because high mass stars are more massive, it goes beyond that and it leads you to neutron degeneracy pressure. So what happens is that all the electrons and the protons that are in atoms actually fuse together due to being crushed together by gravity, and they form neutrons. So basically, everything in the star now is now neutrons, and once that happens and neutrons can't move, the collapse stops. But they are extremely dense, so a teaspoon amount would weigh as much as Mount Everest. And there's actually two types of neutron stars. There are pulsars, which are rapidly rotating neutron stars because when a star collapses, it's already rotating. And basically, once that happens, when it collapses into a neutron star, it's going to be rotating itself. And it's extremely fast. So, similar to how an ice skater squishes in her arms closer in order to spin faster, a neutron star does the same. It becomes smaller and more dense and moves faster. In fact, the fastest pulsar has a rotation period of about 1.6 milliseconds, or about 38,500 rotations per minute. And then you have magnetars, which is an almost neutron star. So it's a highly dense, larger than usual neutron star that has a magnetic field that's 100,000 times greater than that of Earth's. So if you were to get too close to one, it would actually pull all the electrons from your atoms, because magnetar has the word magnet in it because because it will attract anything that has involving electromagnetism in it. So basically, electrons, it will just pull all of your electrons out of your atoms, and you would just turn into probably a puddle of goo. Let's move on to the second remnant of a high mass star, and it's the more fun one: black holes. And black holes only form by collapsed stars of over 20 solar masses. So if you're a high mass star and you have between 5 and 20 solar masses, you get a neutron star. Any greater than that, the whole thing just collapses completely. You go past electron degeneracy pressure, you go through neutron degeneracy pressure, whole thing goes. And all you get is just a giant hole through space and time. And these things can be massive. And due to the amount of gravity it has, nothing that goes past the event horizon can come back out again. Matter, space, even light. And as you can see in the picture of this more famous one right here, you can see all this matter is actually accreting around the black hole. And if you look at it, you can see at the bottom of it, it's brighter than what's in the back. And the reason for that is because the light is redshifted. So basically, the faster the light is moving away from us, the more redshifted it becomes until it becomes dimmer, dimmer, redder, redder until it disappears. And the reason why the image looks like this is because the brighter spot, the brighter area is basically the light that's closest towards us, while the dimmer area is farther away from us. And because black holes have gravitational lensing around it, we're actually seeing behind it. So really, the brighter part is more flat on towards us, while the upper part is looking behind it. And actually, the event horizon is much more smaller than even that black area. It's just that the light is so redshifted, we just don't see it anymore. And then, of course, there is the singularity, which is basically the infinitesimal point in which the black hole is at. So basically, everything gets squashed down into an infinitesimal point. And if you remember back at the beginning of this presentation, I said that our universe started off as an initial singularity. So there's actually a theory that inside of each black hole, the singularity is actually its own universe. So basically, if that's the case, then that means our own universe, as vast as it is really just inside of a black hole of a much larger universe. And that every black hole that we've discovered is really just its own universe. Well, there's food for thought. Existential crisis. And currently, the largest known black hole is TON 618, which is about 66 billion solar masses. And black holes have a lifespan of about 10 to the power of 67 to 10 to the power of 100 years, which is a Google years. So now that you know what a Google is, now you can use that. And it evaporates due to Hawking radiation. So basically what happens is that there are virtual particles in space that pop in and out of existence, and they are their own matter and antimatter particle. So what happens is that a virtual particle forms along the base of the black hole, and what happens is that one particle falls into the black hole and the other one shoots off, because since because they just shoot off against each other. And basically, what happens is that whenever one particle shoots off into space, it actually drains energy from the black hole. And for all intents and purposes, a black hole evaporates because once it loses energy, it'll basically just shrink down and shrink down and shrink down until it finally disappears after 10 to the power 67 years for the small black holes and 10 to the power of 100 years for the supermassive black holes until it disappears in a burst of light. Well, that was a lot to learn. Now let's move on to the fun section. Hypothetical stars of the past, present, and future. The first star on the list are dark matter stars, and these would be theorized to be the first quote-unquote stars before conventional stars as we know them. And they would have formed in the early universe. And they would have been made of hydrogen, maybe some helium, and oddly enough, 0.001% of dark matter. And if you remember what dark matter is, it's basically these theorized particles that exist that do not interact with matter whatsoever. And the only reason why we know they exist is because of their gravitational influence on normal matter. The reason why dark matter would be inside this star is because the universe would have been much denser in the early universe. Because remember, the universe is continually expanding. So if you go back far enough, the universe would have been much denser in terms of matter. And with dark matter being in the universe, it would have been clumped together more, and maybe even interacted with normal matter. Normal matter, maybe. So, like with a normal star, you have these clouds of hydrogen, helium, and dark matter, and eventually, due to its own mass, they would start collapsing into balls. And in the core of it would, of course, be the dark matter. And with dark matter, if there's also a dark matter antiparticle, there would be an annihilation. And here's the thing, dark matter annihilation is 100% efficient because with all the energy that you get through nuclear fusion, all the energy that's produced is only about 1% of the that's all that's usable, about 1%. But with dark matter, if it's annihilating with its own antiparticle, it's at 100% efficient. So basically, it works the same way as nuclear fusion, where basically you have this energy output surrounding the core, and that's keeping it from just simply collapsing under its own gravity. And these things would have been massive. Dark matter stars would have been between 4 and 2,000 AUs in diameter, maybe up to 10 million solar masses. And the thing about it is that there's no known upper bound for how large these stars can get. And already 2,000 AUs is equivalent to 3% of a light year in diameter. That's how large it is. So it would have just been a cloud, 3% of a light year of nothing but star. And the reason why there's no known upper bound is because as long as there's dark matter for the star to burn, it will just keep growing bigger. Yeah, the early universe is kind of weird, isn't it? Now let's move on to something a little bit more practical. Here is UY Scuti. It is the largest known star, and of course it's a red supergiant. Its radius is about 1,700 times larger than our Sun, and as you can see in the picture on the right, Earth's Sun is nothing but on the bottom right, you can see that Earth's Sun is nothing but just a pixel. Well, just a little dot. It's nothing. It would be swallowed by UY Scuti, and it probably wouldn't even notice. And if you were to travel at the speed of light, it would take you about 7 hours to travel its circumference compared to only taking about 14.5 seconds to travel around the sun. So this thing is massive and makes our sun look like nothing. And this is a quasi-star. Yeah, just drink it in. Oh look, there's our friend Beetlejuice, the one who's making so much noise in the news recently. And there's UI Scooty, who thought he was all big and bad. And I'm pretty sure if you get a microscope, well, magnifying, no, microscope would be more accurate. I'm pretty sure a sun is in there. Yeah. Why is it so big? Well, quasistar is a type of population 3 star, and it would have been the largest of them. This thing would have had a diameter of about 10 billion kilometers, or equivalent to 66.85 AU, or astronomical units. So that's 66.85 times 93 million. And it would have had a mass of about 1,000 solar masses. Here's what's going on with the quasistar. These stars were already large in terms of population 3 stars. In fact, they were so large that their core actually collapsed directly into a black hole. So you would think it would just go supernova, but no, it doesn't go supernova. What happens is that the core collapses into a black hole, but because of the energy being produced by the black hole swallowing all the matter around it, it actually creates energy. So like a core which is going through nuclear fusion, it actually produces energy that keeps a star from collapsing in on it. And as a result, the outer layers start to expand. And that's one of the reasons why it becomes so big. And like all population 3 stars, this star would have been as bright as a small galaxy. And it comes into question whether or not these would have been the origin of supermassive black holes. Because remember when I was talking about types of population stars, of how it's logical if you start, it has a logical pattern? Well, then this makes sense. Because you could have had a quasi star which would have had a black hole inside of it, and as the black hole started creating more and more material, it would have became bigger, because a quasi-star would last for about 7 million years, and then eventually the entire star will be swallowed up, and in its place you would have a black hole. And all the other population 3 stars that then become quasi-stars, they would have supernovaed, and they would have produced all the gases needed to make the population 2 stars. So what would have happened was that you had a quasi-star, which would have had a huge black hole, and that could have been the center of the galaxy. Then you had the population 2 star surrounding that, and then when they went supernova, then you have the population 1 star surrounding that. So you had the quasi-star being the center of the galaxy, and the population 2 stars being the galactic bulge of the galaxy, and then you have the population 1 stars making up the disk of the galaxy itself. Now let's move to the present. This is a Thorne-Zitko object. This is theorized by astrophysicists Kip Thorne and Anna N. Zitko in 1975. And basically the idea behind this is that you have a giant red star with a neutron star in its core. How does this happen? Well, remember, giant red stars would have been huge, and a neutron star is only going to be like 10 kilometers in diameter. So a neutron star can fit, assuming that the giant star is able to maintain itself and it just doesn't go supernova the second the neutron star comes into contact with it. Because at the end of the day, it's a star. And there's 3 ways of forming, which is until it just basically wraps the entire star around around a neutron star, and that would be considered a vampire star, in which is basically zapping all the gas from a larger star. Or it could be fired into a red giant via supernova. So basically what could happen is that the neutron star is part of a system with a larger star that went supernova, and then a shockwave caused the neutron star to shift and go flying out of the system, until eventually it comes into contact with another red giant and it just gets sucked in and becomes the core of the red giant. Or it could be formed by encompassing, in which basically there's a neutron star, then it just comes in contact with and well, basically a neutron star just slowly rotates inside of a red giant until eventually the red giant just encompasses a neutron star. And there's actually one candidate, and that is HV2112, which is located in the small Magellanic Cloud, which is about 200,000 light years away. And the way you'd be able to tell that it could be a Thorn Zitko object is by the fact that it has certain properties, that the star has certain properties which stand it out from being just a normal red giant, especially when you have basically a dense ball of neutron inside of it. Is going to be standing out. Now let's travel into the far, far future, and then we have the frozen star. And these stars can form in the far future due to the increased metallicity in the universe. Because remember, early universe, there was no metals in it. And it took the supernovas of population 3, 2, and even 1 stars in order to add all this metal. Well, as the universe continues, more and more metal is going to enter into the universe. So the metallicity of the universe is going to increase. And as a result of the high metallicity, it allows stars to form at much lower masses, which is the reason why, if you go to the early universe, population 3 stars were so big, because they needed to be that large in order to be a star. But as you go farther and farther in the future, it does not have to be so big. So as a result, a star, or at least a frozen star, would be no larger than Jupiter. Yet it would still have 40 times. Yet it would still be 40 times more massive. So, sorry, Jupiter, but no, you still don't make it. Even if you make it to this far future, no, you still won't become a star. Sorry. And the frozen star would have a surface temperature of about 0 degrees Celsius, or about 273 Kelvin, and would have ice clouds. So, whatever civilization that might exist at this far future, depending on the technology they have, they might be able to actually go inside of it, maybe even walk on it, assuming radiation and gravity didn't kill you. And because it has a slower rate of hydrogen fusion in its core, it means that it have a much, much longer lifespan. Even longer than red dwarf stars, which, if you remember, is about, 120 trillion years? This is a black dwarf star, and basically these won't exist until about 1 quintillion years. And basically this is the end result of a white dwarf star, because remember, white dwarf stars form when a low mass star goes, basically just sheds all of its outer layers, and it still has heat on it. But eventually the heat from the white dwarf star eventually erodes away until eventually there's just nothing left, and it just becomes a black, dead ball of gas. But that won't happen for 1 quintillion years. Oh boy, did my jaw drop when I heard the existence of these stars. Well, possible existence. And they are iron stars. And these stars would occur if proton decay does not occur, which would take place in 1.67 times 10 to the power of 34 years. Because particles do have like a half-life, but how long they exist before they split off into being 2 different particles. Now, protons, we're still not sure yet if they decay. But if they do decay, it would take that amount of time in order for it to decay. So if they don't decay, basically what will happen is that all particles that are left in the universe will either fuse or decay into iron 56 isotopes. And remember, iron is the most stable element in the universe. Therefore, all surviving solar masses would become cold spheres of iron. And they will not appear until 10 to the power of 1500 years. Yeah, just imagine that number in your head. And all iron stars won't collapse into black holes until 10 to the power of 10 to the power of 26 years and 10 to the power of 10 to the power of 76 years. Oh, and just to save you the trouble of imagining what 10 to the power of 1500 years is, it's the equivalent to this. Yeah, that number is a lot larger than what you thought it would be, isn't it? And the 13.8 billion years, that's the current age of the universe. So we have a long way to go to get to iron stars. And we finally come full circle as we reach 10 to the power of 10 to the power of 52 years. So iron stars, by this point in time, they are way gone, and none of our supercomputers on Earth can produce this number. Not even close. By this point in time in the far, 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 far future, are projected to produce another Big Bang. And the reason why this happens is because the creation of another universe through a new Big Bang has a non-zero probability. And given a long enough time span, anything that has a non-zero probability will happen. So most likely, by this point in time, after everything's gone, the red dwarf stars, or white dwarf stars, neutron stars, black holes, Thorn-Zico objects, iron stars, frozen stars, all gone. Even particles will be gone, because by 10 to the power of 10 to the power of 40, all remaining particles in the universe are due to collapse into black holes. A new universe is going to form through a new Big Bang. And the process in which stars have been formed will start all over again. And this is the end of my presentation. We started where we began. Thank you.
Okay, thank you again, Bryan Hill deGrasse Tyson, for that excellent presentation. There was certainly some categories of stars that I have never heard of before, and I hope this presentation stretched your thinking just as much as it did me. I mean, this is really a fascinating journey in astronomy. You know, we start off with hypothetical objects, really just mathematical expressions, and then a century later, through discovery and through technological innovation, we're able to not only confirm their existence, but actually photograph them. So who knows where we're going to be a century from now when some of the categories of stars that Bryan covered in his presentation, which are just hypotheticals today in the year 2020, just like black holes were in the year 1920, where we're going to be a century from now in the year 2120. So excellent presentation. Again, thank you, Bryan, for taking the time. Bryan is online, so if you guys are still online, you have any questions or comments, I'm just going to go ahead and bring up the channel here. And if you have anything you want to say, I got some comments coming in. Thanks, guys, for sticking with us. I want to just take a second to give a special shout out to our fans in Portugal. Felipe, you're still up. It's a little past 3. And I know that you're back on our channel. So thank you again for sticking with us and staying up well past, I'm sure, your bedtime. So certainly happy to have our visitors from around the country and around the world sticking with us. So yeah, seeing some of the comments here. If you guys have any questions, feel free to bring them up now. While I do that, just want to remind you guys that, again, if you if you're interested in joining our mailing list, go to this website here. Go to joinmas.com and just enter your name and your email address. And again, we'll just add you to our email list, our email notification list. So yeah, feel free to go there if you're not on our email list already. Enter your name and email address, and we'll send you notices about upcoming meetings and also upcoming events. Probably going to be doing this for a while. You know, we're just sheltered in place right now. We're riding out the COVID-19 pandemic, so we may be doing this for a little while for the unforeseen future. I'm not sure when we're going to be able to reconvene at Christian Brothers University where we normally meet. So I sincerely doubt we'll be back in June. We may be, but I have a feeling that the way things are going to go for the foreseeable future is groups of 10 people or less are going to be banned, and we're just going to have to take the necessary precautions. So this may be our routine for a while. Again, we're shut down in May. I know it's a bummer because May is one of the nicest months of the year. We're just going to continue to monitor the COVID-19 situation week by week, discuss it in our next board meeting. And then if and when we do, and we will eventually get back to doing public observing sessions, we'll have to do it under the direction of, strict social distancing guidelines, which we will outline if and when that time comes. But for now, temporarily, we're shut down. Keep an eye on your email because this situation is continuing to unfold week by week. And, things could change or develop literally on a week by week basis as we try to figure out how to make adjustments with just these unprecedented times. So again, tentatively, if you're in Memphis, June the 13th is the date that we're targeting for our next dark sky observing session to open things back up. May the 16th, canceled for Village Creek. May the 23rd, not going to be doing a public observing session at Burton's. But if those nights are clear, get out, whether it's at home, in your driveway, or you can get to a dark sky site conveniently, not too far from where you live. This is a beautiful time of the year. This is the time to get out as much as you can. Obviously, it's being as safe and as cautious as you can. So yeah, this is not necessarily the time to just stay inside and shut down. Get out and take advantage of the nice weather as much as you can. It's good to rejuvenate the spirit and the soul. So we'll send out an email notice soon regarding our next program for June. Again, we meet the first Friday of every month. Formerly at Christian Brothers University, now we're streaming our meetings online. We'll have this entire meeting up on our YouTube channel by the weekend. So if you dialed in middle of the presentation or couldn't hear the whole thing, we'll have this presentation up on our YouTube channel. Again, guys, if you're new to our channel, please take a second to subscribe and like this video. Subscribe to our channel, like this video. Get on our mailing list. Again, it's joinmas.com. We'll send you more updates. And if there are no other questions or comments, again, thank you guys for sticking with us tonight. It's about 9:30 Central here in Memphis, Tennessee. Special shout out again to the Seattle Astronomical Society. Thank you guys for taking a moment to join us, as well as our visitors from around the world. And again, just want to encourage everybody to stay safe, stay healthy, continue to exercise vigilance, and abide by the guidelines until we get through this. And we will get through this together. We are alone together. This is just a moment in time, unique moment in history. And everybody stay healthy. Everybody stay safe. And we will see you guys 1 month or the first Friday in June, which is our next regularly scheduled Memphis Astronomical Society meeting. So for Jeremy Veldman and the rest of us at the Memphis Astronomical Society, signing off. We'll see you at our next meeting. Have a great night. Thanks again.